Whether you're here to learn, unwind, or simply drift into a peaceful doze, you're in just the right place. Tonight, we'll be following a gentle trail of moonlight across the sea, exploring how the moon, yes, that glowing pebble in the sky, quietly tugs at the oceans below. It's a slow, steady pull, not unlike the way your eyelids might start to feel, just about now. Before we set sail on this lunar voyage, I'd love it if you gave the video a little like. It helps this cozy corner of YouTube reach more fellow wanderers. And if you feel like joining me for more starlit science in the future, tapping that subscribe button is always appreciated. If you're feeling extra chatty before the snooze kicks in, let me know in the comments where you're watching from and what time it is in your part of the world. It's always a joy to see this little sleepy community stretch across time zones. Now, I'll do my best to keep things soothing and not too riveting, but if you do find yourself lying awake thinking about tidal forces and orbital mechanics, well, at least you'll have some solid science to ponder while the moon does its thing. So settle in, let the blankets wrap around you like warm sea foam, take a deep breath and let's begin. Picture this, a beach at dawn. The sky is barely blushing with light, the wind is whispering, and the waves are slowly creeping up the sand like they're stretching after a long night. It's peaceful, rhythmic, almost like the ocean is breathing in and out. In and out. That's the tide. Quiet, constant, ancient. But beneath this calm ritual is a story of immense, invisible forces. A kind of planetary choreography that's been going on for billions of years, and the star of the show, our very own moon. The tides are, in the simplest terms, the regular rise and fall of sea levels across the globe. But they're not quite as simple as water sloshing back and forth. They're not caused by the wind, or passing ships, or the ocean getting bored and deciding to move around. They are the result of an intricate gravitational dance between the Earth, the Moon, and the Sun. A cosmic push and pull that shapes the very rhythm of our planet. Twice a day, every day, the sea retreats from the shore and then returns. This is something so regular, so dependable that humans have been tracking it for thousands of years. Ancient fishermen in China and Mesopotamia planned their harvests by it. Medieval monks timed their prayers to it. Entire cities have been built and sometimes lost because of it. But why does it happen? Why does the sea keep coming and going like it's late for something? To understand that, let's imagine the Earth not as a solid ball, but as a water balloon wrapped in a thin layer of land. Now picture the moon, silvery, steady and quietly determined, pulling on that balloon with its gravity. It's not a yanking, dramatic pull, but a subtle, continuous tug. The moon's gravity pulls the ocean toward it, creating a bulge of water on the side of Earth that's facing the moon. That's our first high tide. But here's where it gets weird in a fascinating bedtime story kind of way. There's a second bulge on the opposite side of the Earth, the side facing away from the moon. Wait, what? How can the moon be pulling water toward it and creating a bulge on the far side? This is one of those moments where the universe seems like it's showing off. While the moon's gravity pulls water toward it, the Earth itself also gets pulled slightly toward the moon. But the water on the far side lags behind a bit, like a sleepy cat refusing to follow the rest of the household. This creates a second bulge, not because the moon is pulling the water away, but because it's not pulling it as hard as it pulls the Earth's centre. That gentle difference in force, what scientists call a tidal force, stretches the oceans into a sort of oval shape. One bulge faces the moon, the other faces away. As the Earth rotates beneath this watery distortion, different parts of the world move into and out of these bulges, experiencing high and low tides in a rhythmic pattern. It's gravity's quiet masterpiece, and all of this is happening constantly. Even as you lie there now, warm under the covers, the moon is pulling gently at the oceans. Somewhere a beach is being uncovered, a boat is rocking a little lower in the harbour, a crab is deciding whether it's safe to come out from under a rock. The time it takes between high tides is about 12 hours and 25 minutes, just a little over half a day. That's because the moon isn't standing still. As the Earth rotates, the moon is also orbiting us, moving a little further along in its path every hour, so each high tide is slightly delayed compared to the one before it. If you were to live by the coast and mark the high tide times every day, you'd notice they're always shifting, arriving later and later by about 50 minutes each day. The moon is nothing if not fashionably late. Now, not every place on Earth experiences the same kind of tidal rhythm. Some places get 2 high tides and 2 low tides each day. This is called a semi-diurnal tide. Other spots might only get one of each, known as a diurnal tide. And in a few places the tides are, well, irregular. These are mixed tides, where high and low tides vary wildly in size. It all depends on your location, the shape of the coastline, and the depth and contour of the seafloor. The ocean, like a cat, does what it wants, but wherever you are, tides are an ever-present hum beneath the surface of life. They regulate ecosystems, they influence weather, they've shaped the migration of animals and the settlement of humans, and the best part, they're predictable. We can chart them years, even centuries in advance. Not many things in life are so reliable. There's something comforting in that, isn't there? That while everything else may feel chaotic, the sea still follows the moon. Twice a day. Every day. Like clockwork. Or maybe more like a lullaby. Repeated softly over and over across the ages. And though we tend to think of the moon as distant and cold, it's hard not to feel a little affection for this quiet companion. It's been shaping Earth's waters since before the first fish wriggled into a tide pool. It's guided sailors, inspired poets, and even helped the early Earth stabilize its spin. Without the moon, our days might be just a few hours long and the climate far more erratic. We owe more to that rocky little sphere than most of us realize. So as you lie there, listening to the soft rhythm of this tale, think of the tides moving far away, unseen but certain. Think of the moon turning its pale face toward us, whispering across space. And think of the water rising slowly against the shore as it has done for billions of years. It is the ocean's breath, the Earth's quiet heartbeat, the moon's gentle pull, all of it part of the same ancient, elegant pattern. And it's still happening right now, even while you sleep. If you were to sit very still, so still that you could feel the thrum of your own heartbeat, you might begin to sense that there's something always happening around you, something constant and invisible. Gravity is the quiet force that tethers you to the ground, holds the oceans in place, and keeps the moon dancing around us like a curious little sibling. It's always there, even when you're tucked under a blanket, sipping tea or brushing your teeth in the foggy glow of early morning. You don't have to think about it. But tonight, we are going to. Because the tides, those gentle sways and sighs of the sea, are really just Earth's oceans responding to a very persistent invitation. Gravity's pull. Let's start with the basics. Gravity is the attractive force between any two objects that have mass. The more mass something has, the stronger its gravitational pull. You and I technically have gravity, although unless you're secretly made of neutron star material, you probably haven't had planets orbiting you lately. The Earth, on the other hand, has a lot of mass, enough to pull us all down to the surface and to keep the moon in orbit. Sir Isaac Newton, the original apple falling understander, first described gravity in the 1600s. He realized that the same force pulling that apple down to the ground was also keeping the moon from flying off into the dark. The Earth pulls on the moon, but here's the twist. The moon pulls back. Not on the whole Earth equally, but especially on the oceans, which being liquid, are a bit more agreeable when it comes to moving around. It's like a slow-motion tug of war, but the moon doesn't yank, it coaxes. It says, "Come here, just a little," and the ocean listens. The result? A bulge of ocean water on the side of Earth facing the moon. That's one high tide, and on the exact opposite side of the planet, there's another high tide caused by something slightly more peculiar. Let's talk about the far side bulge for a moment, because this is where gravity gets especially sneaky. While the moon pulls the water closest to it the hardest, it also pulls the Earth itself, rock, mountains and all, just a bit less hard than the near side water. The water on the far side, however, is barely feeling the moon's tug at all, so relatively speaking it lags behind. The result is that Earth's mass shifts a bit toward the moon, and the far side's water seems to stretch away. Voila, a second bulge. It's not being pulled outward so much as left behind in the moon's slow embrace. This concept, differential gravity or the tidal force, is one of the most quietly elegant features of our physical universe. It's not just gravity pulling everything in, it's gravity pulling different things differently. That subtle imbalance is what sculpts the tides. To get a clearer picture, imagine stirring a bowl of soup while holding a slice of bread on the surface. As you swirl, the soup behaves differently depending on its distance from the centre of motion. The bread might lag or surge depending on how you move. The ocean does something similar as Earth spins beneath the moon's gravity field. And yes, Earth is spinning. While the moon orbits us roughly once every 27.3 days, Earth completes a full rotation in just under 24 hours. So from our perspective, it seems like the moon is gliding across the sky each day. But in reality, we're rotating beneath that gravitational pull. As different parts of the Earth pass under the two tidal bulges, one facing the moon and one opposite it, we experience high tides. Between those bulges, the water levels drop and we get low tides. It's a graceful planet-wide pirouette, and it never stops. You might wonder, if gravity is so strong, why aren't the oceans simply flinging themselves at the moon? Why don't we see dramatic sloshing or waves leaping into space? The answer is balance. The same force pulling water toward the moon is also met with Earth's own gravity, anchoring the oceans in place. In fact, the entire Earth-Moon system is held together in a stable, harmonious orbit by the very laws of motion that Newton figured out while presumably dodging apples. There's also centrifugal force at play, another ingredient in this planetary recipe. As the Earth and Moon revolve around their shared centre of mass, which isn't the Earth's centre, but a point slightly beneath its surface, the rotation creates a slight outward force. This force helps create the bulge on the far side of Earth, balancing out the Moon's pull. The result is two high tides, even though there's only one moon. Now, gravity isn't just playing games with water, it's also subtly deforming the Earth itself. The solid ground beneath our feet actually rises and falls by a few centimetres due to these gravitational forces. It's called Earth tide, and while it won't flip your coffee table, it is a reminder that nothing on our planet is truly still. The moon's role in this grand affair is central, but it's not the only actor. The sun also exerts gravitational force on the Earth, and though it's nearly 400 times farther away than the moon, it's also vastly more massive. Its gravitational influence is about half as strong as the moon's when it comes to tides. When the sun, moon and Earth align, during full moons and new moons, their combined pull creates higher high tides and lower low tides. These are called spring tides, not because of the season, but because the water springs farther than usual. When the sun and moon are at right angles, their gravitational forces partially cancel out, leading to neap tides, which are more moderate and subdued. So yes, the sun is involved too, but the moon, with its closeness and subtle persuasion, remains the tide's main conductor. As you listen, you may feel the weight of all this science, or perhaps the weightlessness of it. These forces are vast and ancient, but also gentle. They don't roar, they don't rush, they glide across our planet in quiet persistence, pulling oceans, nudging continents, and rocking boats in harbours all over the world. Gravity is the universe's soft whisper, and the tides, they're the sea's slow reply. The moon pulls the ocean toward it, so you'd expect one high tide a day, right? One big watery bulge following the moon like a loyal sea dog. Logical, tidy, satisfying. And yet, reality, as usual, has different plans. Most places on Earth get not one but two high tides every day. One when the moon is overhead, and another about 12 hours later, when it's on the other side of the planet. How can that be? At first glance, it sounds like the moon is somehow pulling on both sides of the planet at once, which seems suspiciously like cheating. But this is one of those places where physics slips on its moon glasses and does something elegantly weird. Let's begin with a gentle reminder. Earth is not a perfectly rigid ball. Our planet, and particularly its oceans, behaves more like a squishy, spinning, sloshing sphere. When the moon's gravitational pull reaches us, it doesn't tug on the planet evenly. The water on the side closest to the moon gets pulled more strongly than the Earth's centre. Meanwhile, the Earth's solid mass, mountains, forests, snack cabinets and all, gets pulled more strongly than the ocean on the far side. This uneven pulling, what scientists call a differential force, is at the heart of the tidal mystery. It's not that the moon is stretching the oceans like taffy. It's that different parts of Earth are falling toward the moon at different rates. The result? The water on the near side rushes toward the moon. The Earth's body shifts a little toward the moon too. And the water on the far side is left behind, forming a second bulge. Imagine holding a giant water balloon in both hands and spinning in a circle. The water inside would slosh and stretch in weird ways, not because you're squashing it, but because of the movement and the forces acting on it. That's Earth, sloshing gently, obediently under the moon's steady gaze. So, two bulges, one on the moon-facing side and one on the opposite side. As the Earth rotates, different places pass through these bulges, giving us 2 high tides a day. In between those high tides, we get low tides when the water has receded, pulled toward the bulges elsewhere on the planet. But wait, if the tides are caused by these 2 bulges and Earth rotates once every 24 hours, shouldn't each high tide come exactly 12 hours apart? In theory, yes. In practice, not quite. Tides don't run on the Earth's clock, they follow the Moon's schedule. The Moon is orbiting the Earth in the same direction that Earth spins, completing one full orbit about every 27.3 days. This means that as Earth spins, it has to turn just a little more each day to catch up with the Moon. On average, it takes about 24 hours and 50 minutes for a spot on Earth to rotate back to the same position relative to the Moon. That's called a lunar day. So each high tide arrives about 12 hours and 25 minutes apart, not 12 hours. That's why if you're vacationing by the sea, you might notice that high tide is a little later each day. It's like the Moon is constantly slipping away, fashionably late as always. Now, not all coastlines play along in the same way. If you lived on a perfectly smooth, water-covered Earth with no continents, the tides would be simple and fairly symmetrical. But we don't live on a perfect water world. We have coastlines, bays, islands, ocean ridges, and seafloor trenches. And all of these shape how the ocean water moves. In some places, like the east coast of North America, the tides tend to follow a semi-diurnal pattern. 2 high tides and 2 low tides each lunar day, with each high tide roughly the same height. Elsewhere, like in parts of the Gulf of Mexico, you might find a diurnal pattern, only 1 high tide and 1 low tide each lunar day. And in still other areas, the tides are a mixed bag. 2 highs and 2 lows per day, but of unequal size. The ocean, it seems, enjoys improvisation. The local geography plays a huge role. Narrow bays can amplify the tidal range, as the water is funneled into a smaller space. This is what makes the Bay of Fundy in Canada such a tidal superstar, with high tides reaching over 16 metres. In contrast, the Mediterranean Sea, almost landlocked, has barely noticeable tides at all. It's like the ocean trying to tap its foot inside a tight shoe. Then there are amphidromic points, places in the ocean where the tide hardly changes at all. These are the quiet eye of a rotating tidal system, where the water doesn't slosh up and down so much as swirl gently around in a circle. If you were to float right over one, you might not even notice the tide was there. It's like the ocean's version of standing perfectly still in the middle of a merry-go-round. And just to keep things interesting, the Earth isn't a perfect sphere either. It's slightly flattened at the poles and bulged at the equator. That means gravity varies slightly across the globe, further tweaking the behaviour of tides. So the reason we experience 2 high tides per day isn't just the Moon pulling at the water like a marionette. It's the result of a complex interplay between the Moon's gravity, Earth's rotation, centrifugal forces, and the unique shape of our planet's oceans and continents. It's less like a metronome and more like a very well-practiced slow-motion waltz, one that's been going on for billions of years. And all the while the water obeys. It shifts and surges, retreats and returns, flowing in step with the Moon's persistent pull. It's a cycle so reliable that sailors have trusted it for centuries, so delicate that a changing coastline can alter its rhythm, and so subtle that you can stand on a beach, toes in the sand, and never feel the force pulling the whole sea toward the sky. But it's there, quiet, invisible, and constant, like gravity, like time, like the Moon rising in the east once more. If the Moon is the headliner of the tidal show, then the Sun is the special guest star with a powerful voice, one that doesn't sing quite as often but can still shake the house. While the Moon is the main driver of tides, the Sun also plays a crucial role, adding its own gravitational influence into the mix. Together, they create moments of dramatic crescendo and hushed interlude in the endless song of the sea. Let's begin with the Sun's credentials. It's big, really big, about 27 million times more massive than the Moon, in fact. But it's also much, much farther away, about 400 times farther to be precise. And here's where things get interesting. Because gravitational pull weakens with distance, the Sun's effect on tides is weaker than the Moon's. Despite its tremendous size, the Sun only contributes about 30 to 40% of the tidal force that the Moon does. Still, that's no small contribution. When the Sun and Moon work together, the tides grow bolder, stretching farther up the shore and plunging lower in retreat. These moments are called spring tides, though they have nothing to do with the season. The term spring here comes from the Old English word springen, meaning to leap. During spring tides, the ocean quite literally springs into action. Spring tides occur during full moons and new moons, when the Earth, Moon and Sun fall in a straight line, what astronomers call syzygy. It's a fun word to say and an even better concept to picture. Imagine the three celestial bodies aligned in space, gravity pulling from two directions in perfect harmony. The moon's tug and the sun's pull combine to create higher high tides and lower low tides. The tides range increases, the contrast sharpens, and coastlines feel the difference. A full moon spring tide occurs when the moon is on the opposite side of the Earth from the sun. The sun pulls on one side, the moon pulls on the other, and Earth finds itself in the middle of a gravitational tug-of-war. Meanwhile, during a new moon spring tide, both moon and sun are on the same side of the Earth, pulling together like two teammates rowing in sync. In both cases, the result is a dramatic amplification of the tidal range, waves that reach farther and leave more sand behind, and then there are the neap tides, the ocean's gentle exhale after the excitement of the spring tide. These occur during the first and third quarters of the moon, when the sun and moon form a right angle relative to the Earth. Instead of reinforcing each other's gravitational pull, they partially cancel each other out. The sun tugs one way, the moon tugs another, and the ocean caught between the two shrugs and settles into a milder rhythm. Neap tides are characterized by lower high tides and higher low tides, more moderate, more restrained. The tide's usual drama is toned down to something more subtle and relaxed. In a way, it's the ocean taking a nap between high-energy performances. This monthly cycle of spring and neap tides repeats with the moon's phases, roughly every 29.5 days, so twice a month the tides stretch higher and lower than usual, and twice a month they mellow out. It's a reliable cosmic beat that the oceans follow like a natural clock, and what a clock it is. For centuries, sailors, fishermen and coastal dwellers have lived by the tide charts, knowing that timing is everything. In the era before smartphones and satellites, spring tides could mean the difference between a safe harbour and a stranded ship. A fisherman in the 1700s might have set out knowing that a full moon meant deeper channels and stronger currents, an opportunity if navigated carefully, or a hazard if ignored. Even today, cities like Venice or London monitor spring tides closely. In Venice especially, spring tides, combined with storm surges and rising sea levels, can bring flooding, transforming narrow alleyways into waterlogged corridors. In London, the Thames Barrier, a marvel of modern engineering, stands ready to be raised during particularly intense spring tides, shielding the city from inundation. But it's not all potential peril. Spring tides are also moments of abundance. Along tidal flats and estuaries, they bring in rich nutrients and push them far inland, feeding delicate ecosystems. Crabs scuttle, birds feast, and plants rooted in salty mud breathe deeply, knowing their time has come. On a more personal scale, people still time their beach visits to the tides. During low tide, whole new worlds open up, tide pools brimming with starfish, sea anemones, and tiny hermit crabs. Sandbars appear where there was once only water. Children run gleefully into puddles that seem to belong to another planet. The rhythm of the tide becomes the rhythm of life, playful and predictable. Of course, as with anything involving giant spinning spheres in space, things can get a little complicated. The exact timing and strength of spring and neap tides can be influenced by the elliptical orbits of the Moon and Earth. The Moon's orbit is not a perfect circle, and when it comes closest to Earth, called perigee, its gravitational effect is even stronger. Combine a perigee moon with a spring tide and a strong storm system, and you get what's sometimes called a perigean spring tide, or colloquially a king tide. These are the tides that turn heads and occasionally raise seawalls. And yet, even at their most dramatic, there's something deeply calming about tides. They remind us that the world runs on patterns, vast, quiet cycles that repeat with almost musical precision. The moon waxes and wanes, the sun rises and sets, and the oceans follow their lead with patience and grace. It's easy to forget, as we go about our busy, electric lives, that we're still creatures of a celestial ballet. That the same sun that warms your skin and powers your morning coffee is also gently nudging trillions of tons of seawater across the planet. That the moon, hanging quietly above rooftops and forests, is pulling at entire oceans without making a sound. So the next time you see a full moon rise over the sea or watch the waves slide back to reveal gleaming shells, remember that you are witnessing the pull of cosmic companions, two great orbs moving the waters of the Earth in a duet that never ends. If Earth were as smooth as a cue ball and covered entirely by ocean, tides would be a relatively straightforward affair. 2 high tides and 2 low tides sloshing back and forth with the regularity of a sleepy metronome. But our planet, glorious and complicated, is anything but smooth. It's a lumpy, bumpy, tectonically restless, continent-spotted marble. And those irregularities, land masses, ocean basins, coastlines, underwater mountain ranges, make the tides dance to a far more intricate tune. Let's begin with something surprisingly easy to overlook. Oceans aren't shallow puddles. They're vast, deep and varied. The Pacific Ocean alone is over 19,000 times deeper than your average bathtub, and unlike bathtubs, it has underwater ridges, canyons, plateaus and trenches. All of these features shape the way tidal waves move. Yes, tidal waves, but not like the ones that crash dramatically on the beaches or show up in surfing documentaries. Tides are better described as planet-sized waves, very long, very slow-moving bulges of water that travel around the globe. These waves don't move at breakneck speeds, but they do have enormous wavelengths, sometimes over 12,000 miles long. When they hit the constraints of land, coastlines, peninsulas, islands, they bend, reflect, and sometimes get squeezed, magnified, or dampened. This is why tidal behavior varies so much around the world. Some coastlines experience 2 nearly equal high and low tides each lunar day, semi-diurnal tides. Others get only one of each, diurnal tides, and still others experience a mixed tide pattern, 2 highs and 2 lows, but of differing heights. It all depends on the shape of the seafloor, the position of the coast, and how well the tidal waves can travel through the maze of continental geography. Take the Bay of Fundy in Canada, for example, a narrow inlet nestled between the provinces of New Brunswick and Nova Scotia. This bay is world famous for its colossal tides, which can exceed 16 metres, that's over 50 feet. Why so dramatic? Well, the bay's unique funnel-shaped channels tidal energy into a narrow, shallow area, amplifying the wave in a process not unlike a child sloshing water back and forth in a bathtub. The shape of the coastline matches the timing of the tidal wave so precisely that the water resonates, piling higher with each cycle, like pushing a swing at just the right moment. It's ocean physics with perfect rhythm. On the flip side, consider the Mediterranean Sea. It's nearly enclosed by land, connected to the Atlantic Ocean by the relatively narrow Strait of Gibraltar. This bottleneck severely restricts the flow of tidal energy into the Mediterranean, so the tides there are minimal, often just a few centimetres. If you were to walk along the shore in Nice or Naples, you might not even notice them. The sea just doesn't have room to breathe. Then there are amphidromic points, the quiet centres of the tidal world. These are locations in the open ocean where the tide appears to stand still. Water levels here don't rise or fall significantly. Instead, the tide rotates around the point in a circular motion like water swirling around the centre of a spinning record. These rotation systems, called amphidromic systems, exist in ocean basins all over the world. If you were floating above one, sipping tea in your imaginary boat, you'd barely notice the tide at all. Meanwhile, hundreds of kilometres away, coastlines would be experiencing their daily ebb and flow like clockwork. This rotational behaviour adds yet another layer of complexity. Tidal waves are influenced by the Coriolis effect, the same phenomenon that makes storms spin. As the Earth rotates, moving fluids like air and water are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection helps give tidal waves their circular whirlpool-like movement around amphidromic points. The whole system spins like a lazy water wheel, powered not by gears, but by gravity and the Earth's spin. And then there's the matter of resonance. Just like musical instruments vibrate at specific frequencies, so too do bodies of water. Some coastal regions are tuned, so to speak, to the frequency of the tidal forces. If the timing of the incoming tide matches the natural sloshing period of a bay or inlet, you get resonance, a condition that amplifies tidal range. It's like striking just the right note on a piano string and watching it hum to life. This is another reason why some areas see dramatic tides while others barely flutter. Let's not forget that the shape of the land above sea level matters too. A gently sloping beach will show more dramatic changes in the shoreline with each tide than a steep rocky coastline. The same vertical change in sea level can expose hundreds of feet of beach or merely lap at the same old rock wall. This is why some beaches seem to vanish and reappear like magic, while others look more or less the same throughout the day. Tides don't just affect water level either. they influence currents too. As tidal bulges move through straits, around islands, and into estuaries, they create strong flows, sometimes powerful enough to reverse the direction of rivers. The Severn Bore in England, for example, is a tidal wave that surges upstream in the River Severn, sending brave surfers and curious spectators flocking to its muddy banks. The interaction of tides with geography also shapes marine life. Intertidal zones, the areas that are above water at low tide and underwater at high tide, are some of the most biologically rich environments on Earth. But how wide or narrow those zones are depends on how far the tide goes out. In places with large tidal ranges, entire ecosystems rise and fall with the water, adapting to dramatic daily changes in temperature, salinity, and oxygen levels. All of this is to say, the Earth isn't just a passive partner in the tidal dance. It's an active participant, shaping, distorting, and even amplifying the Moon's gravitational whispers. The solid Earth may seem still and unmoving, but in reality, it's a complex stage, reshaping every note of the tidal melody. So the next time you find yourself near the sea, watch how the waves trace the land. Notice where they reach and how they return. Somewhere beneath your feet is a vast, unseen landscape of mountains, valleys, plains, guiding the ocean in ways you can't see, but the Moon certainly can. Even gravity, it turns out, likes a bit of terrain. The Moon has always been a loyal companion, circling us in silence, glowing with borrowed sunlight and tugging at our oceans like a patient choreographer. But the relationship hasn't always been what it is today. Like all long-term partnerships, the Earth and the Moon have changed each other over time. The tides, far from being a static rhythm, have evolved across the ages. In fact, the tides we experience now are just one brief measure in a much longer song. To understand how tides have changed, we need to rewind time, not just a few centuries or millennia, but billions of years, back to when Earth was newly formed and the Moon had only just been born, likely from the debris of a massive collision between the young Earth and a Mars-sized object named Theia. The Moon emerged from that chaos glowing red-hot and orbiting much closer to Earth than it does now, about 22,000 kilometers away compared to today's comfortable 384,000. With the Moon so close, tides would have been far more extreme. The gravitational pull on our oceans was significantly stronger, resulting in tidal bulges much larger than the ones we see today. Early Earth might have seen tides hundreds of meters high, sloshing in and out with such force that coastlines may have reshaped themselves daily. The ocean would not have calmly risen and fallen, it would have surged and roared. The rapid pace of Earth's rotation back then added to the drama. A day on early Earth may have lasted only 5 or 6 hours. The faster the spin, the more frequently different regions passed through those massive tidal bulges. Imagine experiencing the full high tide to low tide cycle multiple times in a single day. A planet racing beneath a moon that loomed much larger in the sky than it does now, pulling oceans up like a puppeteer with very enthusiastic strings. But nature, as always, seeks balance. Over time, the tidal friction caused by those surging waters began to act like a cosmic brake. Every time the oceans bulged and the Earth spun beneath them, friction between the moving water and the ocean floor sapped a tiny bit of energy from Earth's rotation. That lost energy didn't just vanish, it was transferred to the Moon, giving it a little boost in its orbit. As a result, the Moon began slowly drifting away from Earth. It's still drifting, by the way. Today, the Moon is moving away from us at a rate of about 3.8 centimeters per year, roughly the same speed your fingernails grow. Not exactly racing off into space, but over millions of years it adds up. The Moon's increased distance weakens its gravitational influence on our oceans, gradually making tides smaller and more subdued. Meanwhile, Earth's rotation has been slowing down. Our 24-hour day is a relatively recent development in geological terms. Hundreds of millions of years ago, a day was closer to 22 hours long, and if you were to somehow fast forward a few 100 million years into the future, your grandchildren's grandchildren times a few billion might experience days that are 26 or even 28 hours long. It's a trade-off. As the Moon drifts, Earth slows. The tides become more relaxed, less dramatic, and more like the gentle rise and fall we know today, and yet these changes are imperceptible within a human lifetime. You could sit by the sea every evening for 100 years and never notice the Moon's slow departure or Earth's subtle deceleration. But the record is written in stone, literally. Ancient tidal patterns are preserved in sedimentary rock. In places like the Bay of Fundy and parts of Australia, fossilised ripple marks, layered mud and silt laid down by ancient tides, tell scientists how often the tide came in and how strong it was. Some rock layers from over 600 million years ago that show 400 or more daily layers per year compared to the 365 we now experience. This suggests that days were shorter and years were longer because Earth was spinning faster. These time-stamped sediments, along with coral growth rings and other geological clues, allow us to piece together the history of Earth's rotation and the Moon's retreat. It's like reading a very slow, very patient diary written by the planet itself. But the future of tides isn't just a story of cosmic geometry, it's also tied to Earth's changing climate. As global temperatures rise, glaciers melt and sea levels increase, the shape of coastlines will change. Estuaries may flood, islands may shrink, and new inlets may form. All of these changes will subtly alter how tides behave. In some places, tides may grow stronger, in others, weaker. We're entering a new chapter in the story of Earth and the Moon, one shaped not only by gravity but also by humanity. That said, the Moon is still up there, patiently circling, guiding the tides in its ancient rhythm. It has seen Earth change countless times and will continue to do so. The dinosaurs watched the same Moon that we see today. So did early mammals crawling through ancient ferns. So did our earliest ancestors, standing by shores that no longer exist. And through it all, the Moon pulled at the oceans and the oceans replied. Sometimes with thunderous floods, sometimes with gentle whispers, always in motion. There's a quiet poetry to this evolving dance. Earth gave birth to the Moon through violence, yet they've been locked in a gravitational embrace ever since. The Moon slows Earth's spin, Earth pushes the Moon away, and in return we get tides, the breath of the ocean, the heartbeat of our coasts. So when you stand by the sea and watch the tide slip in or out, you're not just witnessing a local event, you're seeing the imprint of billions of years of gravitational interaction. You're watching a memory that's still unfolding, and you're part of that memory too, just a brief note in a planetary symphony. One where the Moon, ever so quietly, continues to shape the world beneath your feet. As the tide rolls in, it brings more than just seawater. It brings life. It lifts, feeds, and carries countless creatures, great and small, in a rhythm older than bones. The Moon may move the oceans, but the tides move ecosystems, and some of the most vibrant, chaotic, and downright charming places on Earth are built around this watery pulse. Let's start where land meets sea, the intertidal zone. This is the strip of coastline that's covered by ocean at high tide and exposed to air at low tide. It's a place of dual identities, half land, half sea, changing its nature completely twice a day. And for the organisms that live there, life is all about timing, patience, and the ability to cling really well to rocks. Take the common sea star or starfish. To us, it might look like a passive ornament of the seafloor, but it's actually a slow-motion predator. As the tide rises, the sea star ventures out in search of mussels and clams, prying open their shells with a methodical hydraulic-powered grip. When the tide retreats, it clings to a rock or burrows into damp sand to wait for the next wave. This rhythm, feed, retreat, rest, repeat, is choreographed by the tides. Or consider the humble periwinkle snail, which spends its days glued to the surfaces of rocks, sheltering from predators in the drying sun when the tide is out. As the water returns, it reactivates, sliding across wet surfaces in search of algae to graze. Entire micro-civilizations of barnacles, crabs, anemones, seaweeds, and sponges live this tidal lifestyle, each with its own strategy for staying moist, fed, and uneaten. Some of these organisms go even further, syncing their entire biological clocks to the tide cycle. Take the grunion, a silvery fish native to the coasts of California and Mexico. During specific nights of the spring tide, when the water reaches its highest mark, grunions swim ashore, flopping out of the waves in great numbers. They lay their eggs in the wet sand just beyond the reach of the usual tide. The eggs remain hidden and safe until the next spring tide arrives 2 weeks later, washing over the beach once more and hatching them in a frothy, silvery celebration. It's one of the few natural events that makes you say, wait, fish that go onto land to lay eggs? Voluntarily. There's also the horseshoe crab, a creature that looks like it wandered out of the Cambrian period and forgot to update its wardrobe. Every year, around May and June, these ancient arthropods gather en masse on the beaches of the US Atlantic coast to spawn, timing their appearance with the full and new moon tides. These synchronized events are so predictable that migratory birds, like the red knot, have evolved to plan their epic journeys around them. As the crabs lay millions of nutrient-rich eggs, the birds descend from the skies to refuel, gulping down crab caviar by the beakful before continuing their trek to the Arctic. Tides are nature's conveyor belt, especially for nutrients. As water moves in and out of estuaries and salt marshes, it carries with it organic material, microscopic plankton, and dissolved minerals. This makes tidal zones especially productive, dense, rich soup kitchens for marine and bird life. Salt marsh grasses, which tolerate salty water that would kill most plants, grow tall and thick in these regions, helping trap sediment and stabilize coastlines. And it's not just animals and plants that respond to the tides. Whole human civilizations have lived and died by the sea's movements. Ancient communities built fish traps in the intertidal zone, clever rocks arrangements that let fish swim in with the tide and become stranded when the water ebbed. In the Orkney Islands of Scotland, some of these traps are still visible today, worn by centuries of tide and time. On a more domestic scale, many fishing cultures have learned to track the tide like a second clock. In places like Southeast Asia and the Pacific Islands, entire villages structure their daily routines around tidal flows. Boat trips, harvests, shoreline foraging, all depend on knowing when the tide will rise and fall. In parts of northern Europe, where mud flats stretch out for miles, people still walk or drive across the exposed seafloor during low tide to reach islands that disappear at high water. It's a peculiar sight, cars driving along what appears to be the ocean, only for that road to vanish under waves hours later. Even coral reefs feel the tides. Many shallow reefs rely on the ebb and flow to bring oxygenated water to their inhabitants. The tides help regulate temperature and salinity, and during low tide, some reef creatures take refuge in tide pools, small self-contained ecosystems brimming with colour and mystery. A single pool might host sea urchins, clownfish, and bright purple algae, all trapped together like reluctant roommates waiting for the next splash of freedom. And then there are mangroves, those bristly, salt-loving trees that grow in tidal zones from Florida to Bangladesh. Their tangled roots provide safe havens for juvenile fish, protect against storm surges, and trap carbon more efficiently than many forests. Without the tides, mangroves wouldn't thrive, and without mangroves, many coastal communities would be far more vulnerable to erosion and flooding. Tides also shape human emotion, creativity, and myth. They've inspired poetry, songs, and countless metaphors. We speak of the tide turning, of relationships and fortunes ebbing and flowing somehow, of emotions that rise like the tide. This connection between lunar cycles and human feeling isn't just poetic. It reflects our deep, intuitive awareness that we are part of the natural world, even if we no longer watch the water as carefully as our ancestors did. But the moon remembers, and so does the sea. Together, they keep the rhythm going. So next time you stand barefoot on the edge of the ocean and feel the tide pull at your ankles, remember that you're standing in a living clock, one that sets the pace for entire ecosystems, signals the start of ancient rituals, and nurtures life in its countless salty forms. The sea is not just moving, it's listening, and the moon is still calling. The tides may be universal, but the way they express themselves around the world is anything but uniform. Like regional dialects in a shared language, tides vary wildly depending on where you are. Some places experience gentle lapping ripples, others are host to thunderous surges. In certain corners of the planet, the ocean seems to leap from the shore, only to vanish hours later. Geography, topography, and a touch of geological flair all combine to give every coastline its own unique tidal signature. Let's begin with a showstopper, the Bay of Fundy. Nestled between the Canadian provinces of Nova Scotia and New Brunswick, this bay is famous for having the highest tides on Earth. On average, the water level in the Bay of Fundy can rise and fall over 16 metres, that's more than 50 feet. To put that in perspective, imagine a 5-story building being gently filled with seawater and then drained twice a day, every day. No pumps, just gravity and the moon. So why is the Bay of Fundy so extreme? It comes down to something called resonance. The bay's shape and depth create the perfect environment for tidal waves to amplify. When the natural sloshing rhythm of the water inside the bay aligns with the timing of the incoming tide from the Atlantic Ocean, the waves build on themselves like a perfectly timed push on a swing. With each incoming tide, the energy stacks, resulting in a spectacular rise and fall of water. Visitors to the Bay of Fundy can actually walk on the seafloor during low tide, weaving between towering rock formations, only to return a few hours later and find those same rocks half submerged. The transition is so fast and dramatic that you'll find warning signs everywhere. "Please return to shore before the tide returns" is good advice unless you're aiming to star in your own slow-motion rescue drama. On the other side of the world, in Mont-Saint-Michel, France, the tides tell an equally dramatic story, albeit with more Gothic architecture. This medieval abbey, perched on a rocky island off the coast of Normandy, is connected to the mainland by a causeway. During low tide, you can walk to it across the sand. During high tide, the sea surrounds it completely, turning it into a fairy tale island fortress. The tides here can rush in at the speed of a galloping horse, fast enough to sweep away the unwary. Pilgrims and tourists have been caught off guard for centuries, watching their dry path disappear beneath a surge of seawater. Then there's the Severn Estuary in the United Kingdom, home to the famous Severn Bore. This is a rare natural phenomenon where the incoming tide forms a wave that travels up a river, against the current, sometimes stretching for miles. Surfers, kayakers, and brave swimmers gather to ride this single, long, curling wave as it rushes inland. It's a tidal roller coaster, powered by the gravitational clockwork of the cosmos. Not all tidal behaviour is so theatrical, though. Some parts of the world, like the Mediterranean Sea, have barely noticeable tides. The Mediterranean is almost entirely enclosed by land, with only a narrow passage, the Strait of Gibraltar, connecting it to the Atlantic Ocean. This limited access bottlenecks the tidal flow. The result? A tidal range of just a few centimetres in many places. If you weren't paying attention, you might never notice the tide was happening at all. The sea seems still, unchanging, as if the moon's invitation has been politely declined. In stark contrast, the Kimberley coast of Western Australia experiences some of the most powerful and unpredictable tides on the planet. Here, tides can rise and fall by more than 10 metres. In narrow coastal inlets like horizontal falls, this movement creates something that looks like a whitewater river, except it's not a river. It's the ocean, squeezing through two narrow gaps in the cliffs at such speed that it churns into raging rapids. Boats can ride through the falls during the slack tide, but when the water's racing, it's a spectacle best admired from a safe distance or a helicopter. Tides can also shape everyday life in more subtle ways. In Venice, Italy, the tidal cycle is known as acqua alta, or high water. During certain parts of the year, especially autumn and spring, there are high tides combined with winds and atmospheric pressure to flood city streets and squares. Locals walk on raised platforms, and shopkeepers stack sandbags in doorways. While these floods have always been part of life in Venice, rising sea levels and more extreme weather patterns are making them more frequent and severe. The tides are not just a background rhythm here. They're an active participant in urban planning, architecture, and even fashion. Rubber boots are essential. Meanwhile, in the low-lying atolls of the Maldives, even small tidal shifts can have outsized impacts. These islands sit just a few meters above sea level, and the difference between high and low tide can mean the difference between dry land and encroaching water. The inhabitants of such places pay close attention to the moon and its movements, not out of curiosity, but necessity. Their homes, roads, and livelihoods are intimately tied to the ocean's moods. Of course, tidal variations aren't just interesting, they're vital to science. Studying how tides behave in different parts of the world helps oceanographers model ocean currents, predict storm surges, and understand how energy moves across the planet. The way tides interact with coastlines, the seafloor, and one another provides clues about Earth's geology, climate systems, and even its past. By analysing tidal patterns recorded in ancient sediment layers or fossilised shorelines, scientists can learn about historical sea levels, tectonic activity, and changes in Earth's orbit. In all their variety, tides serve as a reminder that while the same forces are at play everywhere, the pull of the moon and sun, the spin of the Earth, the expression of those forces is infinitely diverse. It's like hearing one song played on thousands of different instruments, each with its own tone and tempo. From the thunderous flood of the Bay of Fundy to the whisper of the Mediterranean, the tides move in countless ways. So wherever you are in the world, whether the sea rises gently or with a roar, know that you're watching a local version of a global story. a story told in water and gravity, time and motion. The moon may be distant, but its influence is deeply personal, shaping not just the edge of the sea, but the lives and landscapes that grow beside it. Every day, twice a day, the tides lift and lower vast quantities of seawater across the globe, trillions of tons of it gliding in and out like a breathing planet. All of this movement contains energy, tremendous energy. And for as long as humans have watched the sea come and go, we've wondered, could we use this? The short answer is yes, we can, and in some places we do. Tidal power, also called tidal energy, is one of the oldest forms of renewable energy we've ever tried to harness. It's predictable, clean, and, if you'll pardon the pun, endlessly recurring. The tides won't forget to show up no matter how cloudy the day or still the air. And unlike fossil fuels, they don't run out or pollute the atmosphere. They just keep rolling in. But how exactly do we capture energy from the ocean's rise and fall? Let's go back in time, way back before wires and turbines and even steam engines. Ancient societies in Europe and the Middle East built simple tidal mills, structures that trapped incoming seawater in a pond or basin as the tide rose. When the tide went out, the trapped water was released through a water wheel, turning millstones to grind grain. These were the coastal cousins of river mills, powered not by flowing streams but by the moon's quiet pull. One of the oldest surviving examples can be found in Northern Ireland, the Nendrum Monastery tidal mill, dating back to the 7th century. It wasn't flashy, but it worked, using the daily rhythm of the ocean to help monks make flour, a divine union of celestial mechanics and snack preparation. Fast forward to today and the principles haven't changed much, just the scale and technology. Modern tidal energy comes in a few flavours. The first and most well established is the tidal barrage. Imagine a dam stretched across a tidal estuary like a giant wall with gates. As the tide comes in, water builds up behind the dam. When the tide turns and begins to fall, that water is released through turbines, generating electricity as it flows back out to sea. It's the same idea as hydroelectric dams on rivers, except the river is the ocean and the water goes both directions. One of the best-known examples is the Reims tidal power station in Brittany, France, built in 1966. It's still operating today and produces enough electricity to power around 130,000 homes. That's the kind of renewable energy that doesn't mind if it's raining or the wind isn't blowing. The tide just does its thing too. Then there are tidal stream generators, which are essentially underwater wind turbines. Instead of air, these sleek machines are spun by ocean currents generated by tides. They are placed on the seabed in fast-moving tidal channels, like underwater highways of water, and as the tide flows in and out, the turbines spin, generating power. Because water is about 800 times denser than air, even a slow-moving tidal current can pack a punch. These tidal stream systems have an elegant simplicity. They don't require dams or large-scale infrastructure. They sit quietly beneath the surface, turning with the tide like windmills in a submerged field. Another method being explored is tidal lagoons. These are artificial enclosures built along coastlines. Water flows in and out of the lagoon through turbines, much like with a barrage, but the lagoon can be constructed in places where building a dam across an estuary isn't feasible. It's a way to harness tidal energy without disrupting entire river systems or natural habitats. Despite the promise, tidal energy is still relatively rare. Why? Well, the ocean may be predictable, but it's not exactly user-friendly. Building things in salt water is tough, the environment is harsh and corrosive. Marine equipment must withstand strong currents, storms and barnacles with dreams of permanent residency. Maintenance costs can be high, and installation isn't cheap either. And then there's the geography problem. Only certain places on Earth have tides strong enough to make tidal energy worthwhile. You need narrow straits or deep estuaries with large tidal ranges and fast-flowing water. That's why only a handful of locations, like parts of the UK, Canada and South Korea, are seriously investing in this technology. There are also environmental concerns to consider. Barrages, for instance, can affect fish migration, sediment flow and local ecosystems. Changing the natural flow of tides might alter salinity levels in estuaries or disrupt habitats that depend on the usual ebb and flow. As with any form of energy development, the benefits have to be weighed against the potential costs to the environment. Still, the idea of drawing clean, rhythmic power from the moon's pull is deeply appealing. It's romantic almost. Energy from a celestial body, channeled through the sea and into our homes. There's something undeniably elegant about it. And tidal power has some big advantages. Unlike solar and wind, it's almost perfectly predictable. We can forecast the tides centuries in advance. That kind of reliability makes it easier to integrate into power grids and plan around. It doesn't vary wildly from day to day. The moon, after all, is not known for being spontaneous. In the coming decades, as the world shifts more seriously toward renewable energy, tidal power may play a growing role, especially in coastal regions where the infrastructure can be tailored to local conditions. Innovations in design, materials, and deployment could make underwater turbines cheaper, more efficient, and friendlier to the marine environment. And perhaps one day the sea itself will help power the lights in your kitchen, the train into town, or even the phone you're listening to this on. A quiet energy, drawn from an ancient rhythm moving invisibly beneath the surface. So next time you stand by the water and feel the tide pull at your ankles, remember, there's power in that motion, real power. Not just the kind that moves boats or stirs seaweed, but the kind that could light cities, the kind that starts 384,000 kilometers away, with the moon whispering to the ocean and the ocean answering with every rise and fall. Each night, as the moon glows quietly above, something extraordinary is happening across the surface of our planet. It doesn't roar, it doesn't flash, but it moves mountains of water, literally. This gentle, predictable force is not just a curiosity or a convenience for seaside picnickers. It's a fundamental part of how Earth works. The tides are more than water levels shifting. They are a conversation between the Earth and the moon, a soft, endless dialogue in gravity's language. You could think of tides as the Earth's response to the moon's gravity. The moon pulls, and the oceans lean in. It's not a tug exactly, not like yanking a rope, but more like a slow beckoning, a celestial invitation that the seas have been answering for over 4 billion years. And Earth listens in kind. It responds not just with water, but with motion, with balance, with time itself, because tides don't only affect coastlines, they influence everything from animal behaviour to planetary stability. And at the heart of it all is the moon, quietly keeping rhythm. Let's take a moment to appreciate what a remarkable partner the moon has been. Unlike the sun, which roars with radiation and flares, the moon says very little. It reflects rather than emits. It drifts rather than burns. And yet it's the moon that shapes the daily ebb and flow of the oceans. It does so with relentless consistency, making the same request of the Earth every day. Come closer, then let go. That request creates tidal bulges, as we've explored. But what's especially fascinating is that those bulges aren't perfectly aligned with the moon. Because of Earth's rotation, the ocean bulges lag just slightly ahead of the moon's position in the sky. That tiny misalignment creates a torque, a twisting force that pulls the moon forward in its orbit and simultaneously slows Earth's rotation. It's like the Earth is giving the moon a little push, saying, "Here, take a bit more momentum," and the moon obliques, inching farther away, about 3.8 centimeters every year. As it does, Earth's day lengthens ever so gradually. In a few 100 million years, a single Earth day might last more than 25 hours. This mutual exchange is called tidal locking in progress. Eventually, billions of years from now, the moon might become so distant and Earth spins so slow that the same side of Earth always faces the moon, just as the moon already shows only one face to us. The gravitational conversation would then settle into a quiet, almost frozen pose, a final embrace, but we are nowhere near that moment now. Instead, we live in the golden age of tides, where the moon still circles us, the Earth still turns, and the oceans still breathe twice a day. This rhythm governs so much more than shorelines. Tides influence climate. They help distribute heat and nutrients through the ocean's layers, driving large-scale currents and keeping marine ecosystems oxygenated and alive. Without tides, the deep ocean might stagnate, becoming colder, less dynamic, and less hospitable to life. Tides shape migration patterns, especially for sea creatures that use the lunar cycle as a biological clock. Sea turtles, for instance, often hatch during specific tidal phases to increase their odds of survival. Plankton rise and fall with the tide, feeding fish that feed seabirds that feed everything else. It's a chain of life tuned to the moon. Even human cultures, our calendars, our myths, our sense of time have grown around the moon's pull. Lunar calendars guided early agriculture. Coastal cities evolved around tidal patterns. Entire languages have developed poetic ways to describe the sea's rise and fall, as if recognizing the ocean's connection to something larger and more eternal. The moon has made Earth what it is. Without it, Earth's axial tilt would wobble more wildly, destabilizing seasons and climates. The moon acts like a gravitational stabilizer, keeping our planet spin relatively steady. Without it, we might not have the regular seasons or long-term climate that helped life take root and thrive. The moon gives Earth its composure, its calm, and there's something comforting, perhaps even poetic about that. That something so far away, so silent, can have such a profound, tender influence. That we are connected, quite literally, to something outside our planet. We don't just orbit the sun, we dance with the moon. This gravitational relationship, though ancient, remains deeply current. Our modern world may be filled with artificial light and city hum, but the moon's rhythm still plays on. If you walk along the beach tonight or look out over a harbour, you'll see it. Boats rising slightly on their moorings, wet sand drying in rippled patterns, shorebirds probing the newly revealed shallows for one last snack before the tide comes in again. And maybe, just maybe, you'll feel it too. The slow pulse of the planet, responding to something far away. The moon, ever the quiet partner, continues to shape the tides without fanfare. No engines, no schedules, just gravity, just presence. So if you ever feel disconnected, overwhelmed or unmoored, consider the fact that every few hours the entire ocean rises and falls, guided by a force you cannot see but can always count on. The moon is still out there, pulling gently on the world, and the world answers, in tides, in rhythms, in whispers between moon and sea. And so, as we come to the end of our journey, we return to where we began, standing at the edge of the sea, listening to the quiet rhythm of the tides. Now perhaps you see them a little differently, not just as waves rolling in and out, but as part of a grand, ancient conversation between Earth and Moon. A gravitational duet that has been playing long before we arrived, and will continue long after we're gone. We've drifted through the science, from bulging oceans and spinning Earth to moonlit fish migrations and the slow expansion of time itself. We've visited rocky shorelines and underwater turbines, seen monks grinding grain with seawater and crabs moonwalking their way to reproduction. We've learned that the moon, despite its quiet presence, is one of the most influential forces shaping our planet, and that the tide, for all its calm and repetition, is anything but simple. It's constant but never still, predictable but endlessly varied, a soft-spoken force with the power to shape continents, feed ecosystems, and slow the turning of the Earth. And now, dear listener, as you lie back, perhaps drowsy, perhaps already floating toward dreams, I hope the tides of this story have carried you gently to the place between wakefulness and sleep. I tried not to make it too interesting, but if you're still awake, then at least you've learned something curious about the moon, the ocean, and the dance they share. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like, or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know, where in the world are you listening from? What time is it there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Wherever you are, and whatever the hour, may your tides be calm, your moon be bright, and your dreams be pulled gently by the forces that have always moved the sea. Good night.